All right, well, good afternoon, everyone, or I guess I should say good morning if you're joining us from the West Coast. Welcome to the Water Finance and Management webinar series. This is Andrew Farr, Managing Editor of Water Finance and Management. It's my pleasure to introduce our webinar this afternoon, Best Practices for Commercial and Industrial Meter Revenue Assurance, sponsored by Census, a Xylem brand. This is an excellent topic. Looking forward to today. We've produced a lot of webinars over the years with Census, so we're glad to have them on board with us today. So just a couple housekeeping items before we go ahead and get started. Right now, first of all, we're going to launch a quick poll question. So this is just to help us get an idea of our attendees and who exactly is on with us today. So if you can see that on your screen, please go ahead and submit your answer, and then you can click the blue Return to Presentation button. So following our presentation today, we're going to have a Q&A session with our presenter. So we encourage everyone on with us to submit some questions if you have them. You can do that by typing questions into the questions panel, which you should see on the left-hand side of your screen. You can also maximize that window to view it by clicking the box with the X at the upper right-hand corner of that slide. So like I said, if there's any questions at any time throughout the course of this presentation, feel free to submit some questions and we will try and go through them at the end. So any views or opinions expressed in this webinar are solely those of the presenters and do not necessarily represent those of Water Finance Management or its publisher, Benjamin Media, nor does Benjamin Media endorse any products or methods presented. But what I always like to say is what we do endorse is a good forum for discussion, and that is certainly what we're going to have here today. So without further delay, I'd like to go ahead and introduce our presenter this afternoon, Jeff Zillmer. Jeff is Product Manager for Commercial and Industrial Water Metrology at Census. He has 17 years of engineering and product management experience in the water and lighting industries and served for 6 years as a United States Naval officer. He's an active member of AWWA and holds a Bachelor's of Science in Engineering from the University of Michigan and a Master's in Business Administration from the University of North Carolina. So, Jeff, thanks for joining us this afternoon. Whenever you're ready, go ahead and take it away.
Thank you, Andrew, and thank you all for joining today. Today we're talking about living large, best practices for C&I meter revenue assurance. The agenda, we're going to go over the benefits of large meter testing, talk about testing requirements, talk about the testing process itself, testing frequency, and then finish it off by sharing some testing program success stories. We'll start off with the benefits of large meter testing. And the number one benefit, of course, of large meter testing is revenue protection. 99% of large meters in the ground today are mechanical meters, which exhibit wear and tear over time. This wear and tear could vary greatly depending on what part of the country you're in, the quality of water, but ultimately the wear and tear causes friction that slows down the meter and ultimately causes the mechanical meters to start registering a little bit lower than the actual water that's running through those meters. So a good meter testing program discovers those accuracy drifts and allows you to recalibrate those large meters and protect that revenue stream coming in. It's listed in the AWWA M6 manual that basically the largest 10% of a utility's meters account for 40 to 60% of the consumption and ultimately the revenue coming in from water for that utility. So it's particularly important to keep testing the large meters. The next benefit of large meter testing is asset protection. Utilities spend a lot of money on large meters. It's a large capital investment, so having a good program that regularly tests these and tests or checks not just the meters, but the whole installation as far as in the vault, the plumbing, if you will, the valves and installation around the meter. By regularly checking up on those, you're preserving and protecting that large capital investment. Going back to the revenue protection benefit, just an example here. Assume you have a 4-inch meter. We'll say it's supplying a medium-sized hospital. According to the Energy Star Portfolio Manager Report in October 2012, hospitals typically use 315 gallons of water per bed per day. So about a 300-bed hospital would use about 100,000 gallons of water per day. So that's our first assumption. Next assumption is the cost of a meter test is $500. So that could be the internal cost of a utility doing the test themselves, their labor, the cost to roll a truck, the opportunity cost of the water they're using and not charging the hospital for, or it could just be the cost that they're paying some third party to come out and test the meter. So that's assumption number 2. And then another assumption is the customer water rate is $5 per 1,000 gallons of water. So if you test this, say this test to this 4-inch meter, and you discover a 5% inaccuracy, if you're able to recalibrate that meter, you can recover basically $9,000 of water revenue per year. So it's a substantial number, and that's for a 5% inaccuracy. $9,000 is enough to more than pay for the test and pay for testing of several other meters. Of course, many large meters have the ability to be recalibrated in the field, either mechanically through a screw that recalibrates a vane, or through recalibrating an electronic register. So in this example, if you paid $500 to test the meter and recovered $9,000 of water revenue per year, we're talking about a payback period of about 20 days. So you've made your money back. The money that it cost you to test that meter, you've made back in 20 days for this example of a 5% inaccuracy. Looking to the table on the right, here's shaded yellow. Here's our 4-inch meter, 100,000 gallons per day. We've made our money back in 20 days. But let's say there are no meters in the utility system that are 5% inaccurate. What type of inaccuracy would be required to make a test worthwhile? So this last column here on the right is, let's look at an 8-inch meter, for example. An 8-inch meter running at this same or equivalent flow rates for the size of meter, as little as 0.5% of inaccuracy. If you can test that meter and discover and then recalibrate to fix 0.5% inaccuracy, you've paid for that test over a 60-day payback period. So I would venture to say most utilities probably have some meters out there that are at least 0.5% inaccurate. Next benefit of large meter testing is non-water revenue reduction. Many utilities are tracking and reporting non-revenue water as a metric. Meter inaccuracy is an apparent loss versus a real loss. So it's not a leak, it's an apparent loss, which means that water is actually getting to the customers. It's just not being accounted for, and you're not seeing the revenue for that water. The good news is apparent losses can be addressed with a solid meter testing program. Next benefit of large meter testing is customer perception. Take, for example, this scenario. You have an old meter in the ground. It's been running for 20 or 30 years. Let's say that the meter hasn't been tested recently, and over time the accuracy of that mechanical meter has drifted gradually down to about 85%. So the customer is only paying for 85% of the water they're actually using. Then, let's say a new meter is installed, and of course, at the time of installation, that new meter is going to be 100% accurate. Suddenly, the customer sees the result of this meter install. The customer sees a huge spike in their water bill, even though they know they're using the same amount of water as they were last month or last quarter. So they immediately believe that there's an issue with the new meter, when actually it was an issue with the old meter. So having a meter testing program, a regularly scheduled meter testing can prevent that initial drift down to 85%. And then lastly, the last benefit of large meter testing is the fair and equitable cost of running the utility. This is straight from the AWW N6 manual, actually. The primary reason for meter tests is to ensure the cost of water service is equally distributed among all customers. And also, the same goes for sewer costs of running a sewer system, which is usually tied to water billing. Okay, next we're going to get into the testing requirements. In its most basic definition, testing the meter is flowing a known volume of water through the meter being tested, and then comparing that known volume of water to the consumption registered on the meter that you're testing. It can be done either in a controlled environment, such as a lab with a calibrated test bench, or it can be done in the field with on-site testing. So the requirements for bench testing, of course, you need a calibrated bench test, and then due to the size of the C&I meters, you would need meters with an interchangeable measuring chamber, so you can easily just change the chamber out, take the chamber back to the facility with the calibrated test bench, instead of course, taking a whole meter out to have it tested. Next comes trained personnel. You need people that are experienced and trained in conducting meter testing. And then lastly, but one part that's often overlooked is a system to manage the results. You need a way to record all your testing that's accessible, that you can look back a year from now and see how a particular meter tested over time. It's important for spotting trends. Basically, if you do the test and don't record the results, lost results is the same as no results. Some examples maybe of a data management system. You can have something very complex, like an asset management system that records a lot of data, where the meter is, the manufacturer, how old it is. Or you can have something as simple as an Excel spreadsheet or an Access database that records your meter test results. So that's for bench testing. The other testing method I mentioned was on-site testing. And for on-site testing, you need a portable large water meter tester, such as the Omni V2 shown on the right, fire hoses and test risers. And then you need site equipment that's specific to the site of the meter where you're testing, such as ladders, hard hats, portable lighting, basically anything that you need to access that location where you're testing the meter. And then you also, of course, still need trained personnel. The alternative to doing the meter testing yourself, again, is contracting out the testing. There are testing services that do nothing but large meter testing. Also, distributors and value-added resellers sometimes have the ability to conduct a large meter test. So I went over the equipment and other requirements. Next, we'll jump right into the testing process. So the first part of the process is basically deciding which meters you're going to test and preparing the site for that meter. You want to prepare the site always per AWWA requirements. And then also keep in mind that safety is the most important consideration when you're testing a meter. You want to make sure you're following all OSHA safety precautions regarding air quality if you're working in a vault or a confined space, eye protection, ear protection, fall protection if it's a deep vault. At the end of the day, everybody wants to go home, so safety always comes first. Then you want to consider the order of testing the meters. The correct order is doing the low flow test first, followed by intermediate and high flow tests. If you're testing a compound meter or a fire service meter, those are meters that have two different flow paths. You want to do an additional test, at least one additional test, to test at that crossover rate where the flow goes from going through the low flow to the high flow path internally in that meter. And then if your test results result in you recalibrating the meters, you always want to repeat the testing process after you do the recalibration, just to verify that you had the recalibration had the intended effect of adjusting the accuracy of that meter. So, talk about flow rates next and volumes. There's a lot of different sources or resources to look into to determine your flow rates for which you're running the test. The AWWA M6 Table 5.3 gives good guidance for the high and low flow rates. You also have manufacturer's data sheets that always give a minimum and maximum flow rate for the range of accuracy of that meter. You want to consider the tester capability for your high and low flow rates at which you can test. For the intermediate flow rate, you really want to consider usage-based. And then also the limitations of the meter or the test port. If you're testing a large meter, for example, but the test port is small, you're going to have a limitation of how much water can actually run through that smaller test port. So that's a consideration when determining your flow rate as well. We'll start with a low flow test first. Low flow test rates are going to come from the M6 Table 5.3, also your meter manufacturer data sheet, and also the tester capability. So here's an example. This is a 3-inch meter that we're going to test. If you look at the table in the M6, that says 8 gallons per minute is the flow rate at which you're going to test, and you have to run a minimum of 100 gallons of water for this test. Again, so this is the AWWA M6 manual. But if you look at the data sheet for this particular 3-inch meter, which happens to be an Omni T2, you can look at the flow rates for this particular meter and see that the minimum flow rate, it's accurate all the way down to 2.5 gallons per minute. So you have 8 up here from AWWA, you have 2.5. In this case, you could test down to 2.5 gallons per minute for this 3-inch meter. Once you conduct your test, here's the basic equation then for calculating the meter accuracy for the meter you're testing. You have the volume of the meter under test that you read from the register. You have the volume of the verification meter. So this is your known quantity of water. And then you have to factor in the test meter, the verification meter's accuracy. And then you plug these into your calculator, or there's software that does it, and that determines the calculated meter accuracy for the meter you're testing. That leads us to our first source of error that I want to talk about. Particularly in low flow testing, one of the common sources of error is failing to account for the tester accuracy. So on the right here is a typical flow versus accuracy curve for a turbine type test meter. And as you can see, down here in the low flow regime, the tester accuracy is highly dependent on the flow rate. Over here in the mid flow or high flow, the curve is pretty close to 100%. In this low flow, though, it can be as low as 97%. So by not including that meter tester accuracy factor in the calculation, your calculated meter accuracy for the meter you're testing could be off. Another common error in conducting the low flow test specifically is not running enough water. Let's say you're testing a 2-inch meter, and every that 2-inch meter, the register changes, the impeller turns over, and the register changes every 0.05 gallons. Let's say your test meter, in this example, your test meter is a 3-inch meter where the impeller turns over and changes the register every 1/10 of a gallon, 0.1 gallons. In this case, a 5-gallon test would turn the impeller of the 2-inch meter that you're testing. It would turn the impeller over 100 times. Your register would change 100 times until it got to 5 gallons. For that same 5 gallons of water that's running through the 3-inch meter, it would only turn the impeller 1 revolution and make the register change 50 times. But if you run just a little bit less than that 5 gallons, say you run 4.9 gallons, for example, that 2-inch meter impeller will turn over 99 times. That 3-inch meter impeller won't quite make it all the way around on that last revolution, and so that little volume of consumption won't be recorded on the register of the 3-inch meter. So that could result in as much as a 0.5% error just by not running, not getting that impeller to turn over that last time on the test meter. Fortunately, there's a good solution to this. By just running the test longer and by running more water through the meter, you're reducing the possible error compared to the total volume of water you run through the test. So if you follow the AWWA M6 manual, particularly the minimum flows for that low flow testing, the minimum volumes for that low flow testing, you should be fine just running the test longer, running more water during the low flow test. Next, we'll get into the intermediate flow test. Your resources for determining the flow rate for the intermediate flow, again, the M6 table 5.3, the meter manufacturing data sheet, and then a usage-based method for determining the flow rate. So I mentioned the M6 table. It actually doesn't contain values for the intermediate flow rate, but what it does say is you use 3 to 10% of the manufacturer's rated maximum flow of that meter. So you have to then refer to the manufacturer data sheet, look where the maximum rated flow is, and then select a flow range or a flow rate between 3 and 10% of that value for your intermediate flow test. The other method, and probably the better method, is going to a usage-based intermediate flow rate. And you can get your usage data from a data log, AMI data, even billing data. In this example, I'll compare why AMI and data log data is much better than billing data for determining the intermediate flow rate. So let's say you have a business. We'll say this is a car wash, and the table to the graph to the right shows the water usage for the car wash over a 24-hour period. So from 9 p.m. until 7 a.m., very little water used at the car wash. Starting at 7 a.m., they open up, and people start washing their cars. Pretty steady throughout the day at about 100 gallons per minute usage from the car wash. You have some spikes in the morning. You have some spikes at lunch when good people of the world are washing their cars. And then you have some spikes, another spike kind of at the end of the day when people are washing their cars on their way home. If you looked at billing data for a month of this usage pattern, you would see that the average gallons per minute is between 50 and 60, where this blue line is on the graph. But if you look at the hourly usage data, at no time during the day is that business using 50 to 60 gallons per minute of water. They're either using 1 gallon a minute when they're shut down, or 0, or they're using 100 gallons a minute. So for this example, you'd want to look at AMI data or download a data log and choose to run your intermediate tests at 80 to 100 gallons per minute. Probably 100. That's where most of the usage is throughout the day. One common source of error for the intermediate flow rate, particularly, is testing at crossover. You want to make sure that if you're testing a compound meter, that you do not pick a flow rate for your intermediate flow test. You don't want to pick the rate at the crossover point of the meter. And that's right here where this dip is. It typically represents the point in the compound meter where the accuracy falls off on the low flow side, which is typically a positive displacement meter, and then before the accuracy picks up on the high flow side of the meter, which is typically a turbine meter. So thing to avoid there is testing your intermediate flow rate at the crossover frequency or crossover flow rate. And you can find that in most of the manufacturer data sheets, what that crossover frequency or crossover flow rate is. And then on to high flow. High flow, you can get your flow rates from the M6 table, from the manufacturer data sheet. Also keeping in mind the tester capability at high flow and the limitations of how much water can flow through the test ports of the meter that you're testing. So max flow rates are a little bit of a challenge, or can be a challenge for very large meters, just because it's difficult to test a meter running 5,000 gallons per minute. So the M6 manual does address this. It says experience has shown that when most meters begin to wear or lose accuracy, it occurs at lower flow rates rather than the higher. If a meter is performing accurately up through the lower 25% of its capacity, of its max flow rate, it will typically test accurately through the rest of the range. This is typically true of the very large meters, which is what we're talking about. So this basically says that you don't have to test your CNI meters at their rated max flow. If you test the meters at 25% of that max flow, that's representative of an accuracy test done at that max flow rate. And then taking this even one step further, here is a flow curve for a 10-inch meter. with a max flow rate of 5,500 gallons per minute. 25% of that is about 1,375 gallons per minute. But let's say your tester only can test at a maximum of 500 gallons per minute. Well, what's the difference between the accuracy of this meter at 500 gallons per minute, which is right here, and the accuracy at 1,375 gallons per minute? It's barely noticeable, if anything at all. So even 25% of the max rated flow is, if you can't get to 25%, the curve really becomes linear at much less than 25%. Even down to 10% of the max rated flow rate, you could use a flow rate for that high flow test and still be very accurate in your calculation for that meter test. Other challenges and sources of error that affect all of the different tests, low, intermediate, and high, misreading the registers. Of course, if you misread the register, then your calculations are going to be off and your calculated meter accuracy is going to be off. And then also leaks on the downstream side of the meter. If you can't isolate that meter 100%, you're going to have some water that's going through the meter, the meter being tested, and sneaking past that isolation valve. That water is not going through the test meter, so that affects your known volume of water that you're using in that meter accuracy calculation. And then we get to the recalibration. Once you've done all your testing, your low flow, your intermediate flow, and your high flow testing, as I mentioned, many C&I meters allow or have the capability to recalibrate in the field, either by using a screw that turns a vane mechanically, or an electronic recalibration using the electronic register. When you add a recalibration factor, you want to compare the accuracy of your test results from all three of your tests with the AWWA guidelines, the M6, and then adjust the calibration of that meter so that you're within those guidelines at all of the different flow rates. So here's a turbine meter example. Let's say you did your low flow test, your intermediate flow test, and your high flow test, and you calculated accuracy of 94%, 99.5%, and 98.3%. So the 94% at low flow is not within the guidance, because that guidance for low flow is 95 to 101.5%. You're in spec here, and then your high flow, you're a little bit low because the AWWA standard is 98.5 to 101.5%. If you added a plus 1% recalibration factor, you would bring all of these tested accuracies within the AWWA standard specs. And actually, you could add up to a 2% recalibration factor, and all of these would still be in spec. You wouldn't be able to add more than 2%, even though this low flow recalibrated accuracy you would expect this to be 96%. You can't add a higher calibration factor, because then this would push the 101.5% and the intermediate flow accuracy up above the limit. So you'd have to add at least 1% recalibration factor, but no more than 2% in this example. Next, we're going to talk about testing frequency. So testing frequency varies widely. It's most dependent on the water characteristics, which can change from region to region, state to state, even town to town. And by water characteristics, I mean the chemical makeup, the physical makeup of the water. Does it have dissolved solids in the water? is it raw water, coming from a lake or a stream, or a well? And typically, harsh water requires more frequent testing. Makes sense. It's also influenced by the cost of the water. Of course, the higher the cost of the water, it increases the necessity and the importance of testing. And of course, the revenue generated by that higher cost water pays for the testing itself. Some common practices for determining the testing frequency of your large meters. Based on revenue production, some utilities test the top 10 to 20% of their consumption meters every half a year to every 2 years. Another method is just picking a specific number of accounts, such as the top 25 accounts, and testing those meters every half year to 2 years. And then also designating a percentage of the revenue from each meter that goes back into testing that meter. So this would, if it costs $500 to test a meter, for example, and you want to designate 1% of revenue generated from each meter to going to test that meter, you're going to generate that $500 faster on your larger meters and test those meters more often than you would on some of your smaller meters, like an 1.5 or 2 inch. Other common practices, one to avoid is determining your testing frequency based on the size alone. This is really straight out of the N6 manual. Because you can't arbitrarily, because you don't know where the water characteristics of your location, the N6 manual says you can't arbitrarily pick a period based on a meter size, just because every system's water quality is different. So this method is not recommended. However, if you refer back to my previous slide, many times the size of the meters is directly proportional to the amount of consumption, the amount of revenue that goes through that meter. So oftentimes the sizing of the meter does have a direct impact on how often you test that meter. But size alone is not recommended. And then the M6 further goes on to say that it has flexible guidance, basically. You can use statistical sampling. You can use it, you can base it on real data, and that makes your data collection even more important. And then some considerations: older meters and those carrying the heaviest volumes are the ones you want to test the most. And registers that are driven mechanically versus magnetically, you also want to test those meters more often. Again, because they wear faster. So a few test program success stories. First one I want to talk about is the Jacksonville Electric Authority. It's one of the largest water and sewer utilities in the U.S. with over 25,000 C&I accounts. They implemented a meter testing and replacement program in 2013, realized that the need, saw that many of their large meters were becoming very old. So they started their program in 2013, testing and data tracking program. They started by testing just a few meters, and those early meter tests and replacement funded and justified the continuation of the program. Eventually, over 400 outdated meters were replaced over a 3-year period, and their results were impressive. They claimed 1 billion gallons of measurable water attributed to their meter testing and change-out program. And then these slides will be available, which includes a link to the full case study. So Jacksonville Electric Authority Florida's largest public utility, recovers 1 billion gallons of unaccounted for water. Another success story is DuPage Water Commission. DuPage is the second largest water system in Illinois with about 800,000 services. Lake Michigan is the sole source of water for DuPage County. This water is purchased from the city of Chicago, and then DuPage distributes it to the communities as a water wholesaler, basically. They have 28 customers and 82 metering stations. They own 208 turbine meters, and they are all 6 to 8 inch meters. So they don't have any residential meters. Their smallest meter is a 6 inch meter. This is their test bench, the picture on the right. And they bench test every meter every year to ensure the accuracy. And their meter testing program has produced an amazing non-revenue water rate of 3%. So 90% of the water they buy is accounted for. And then last customer success story is the city of Cumberland, Maryland. It's a population of 21,000. Their water distribution system is fed by Lake Gordon and Coon. They have two 36-inch mains, about 10,000 service connections, and actually supports customers in 3 different states. They built a case for large water meter testing because they saw their city was in industrial transition with production decreasing. The water value, the cost of water was increasing, and they had a non-revenue water rate of around 50%. So they recognized the need to take action and also wanted to protect their assets. So they started their program. They identified the worst offending meters and replaced them, and that sustained the revenue recovery for additional meters. The lessons learned, their large meter testing program, they learned that success requires commitment to long-term results. You have to make the effort to keep meter testing ongoing and continue investment in new metering technologies. And over a several-year period, they were able to use their meter testing program and replacement program to improve their non-revenue water rate from 50% down to about 15%. So a big improvement from what started as their meter testing program. And they attribute their keys to success, again, to the data management, the way they were able to record and capture and then recall that data to spot trends, consistency, basically picking a program and sticking to it with the methodology and how they test every meter. And then also they noted that a good testing program should pay for itself. So we've talked about the benefits of large meter testing, the testing requirements as far as people and equipment, the testing process itself, testing frequency, and shared a few success stories. So are there any questions?
All right, thanks, Jeff. Great presentation. Yeah, we do have a couple questions coming in. First off, this person here asked, we test large meters when there's a problem, but we don't regularly have we don't have a regular testing program. What are some keys to starting a regular meter testing program?
Good question. Let's see, so going back to the slides I had about the requirements, you need the proper test equipment. So either a test bench in a controlled environment and a test facility, or if you want to do the on-site field testing, you need the portable large meter tester. You also need a way to to train your personnel and get them experience in large meter testing. And then, again, the biggest thing is getting that system, that data management system going, so you can keep track of all this testing that you're doing and not losing any of the data. And that even starts with just basically an assessment, an overall assessment of all the assets that you have in your system, just recording where every meter is, how old the meters are, when the last time those meters were tested or repaired or recalibrated. Once you establish all that information, you can start from there in determining which meters you want to start out testing, which ones are the most likely to be to have some wear and tear that would cause the registers to be inaccurate.
Okay. Another question here on recalibration. So we're wondering if maybe you could elaborate on some of this a little bit more. So are you saying that although the calculated accuracy is not within the acceptable range, you can calibrate and consider it within the acceptable range?
Let me read that. Okay, could you please?
Yeah, you want me to go ahead and repeat that?
Yeah.
Okay, so in terms of calibration, are you saying that the calculated accuracy is not within the acceptable range? If it's not within the acceptable range, can you recalibrate it and then consider it within the acceptable range?
Okay, yes. If the meters that you're testing have the capability to be recalibrated, and say when you do your initial testing, that meter accuracy shows that it's only 95% accurate. If you have the ability for that meter to recalibrate it either mechanically or electronically through the register to basically compensate for the wear and tear that meter is experienced mechanically, then you boost what that register is showing, and you can, by adding that calibration, recalibration factor, you can boost the accuracy up into the acceptable range.
Okay, yeah, that makes sense. Okay, another question here on the test bench. So as I understand it, using a meter test bench is typically not done on site. Is that correct? And if so, can you explain how that works exactly?
Right. So bench testing requires you to either take the whole meter out of the system, which isn't usually practical, or many meters have removable and replaceable measurement chambers or measurement elements. So if you have an extra spare measuring element or measuring chamber, what you can do is quickly exchange those out and bring back the measuring chamber that you take out of that meter back to your test bench and measure that chamber on the test bench. If the meter installed does not have a replaceable measuring chamber, the bench testing is much more difficult because then you'd have to take out the whole meter. Then certainly the on-site testing with a portable large meter tester would be the better way to go.
Okay. So if you're running into an instance where the meter is at the switchover point, how would you recommend dealing with that? Could you use smaller meters or meters in parallel?
If you know where that crossover point is, then you want to avoid testing at that crossover point for your intermediate flow rate. You do want to test at that crossover point just to see where the accuracy is, because even a compound meter has a separate accuracy guideline at the crossover point. in the M6 manual, I believe it's 90 to 103%, which is much wider than the 98.5 to 101.5% accuracy guideline for the intermediate and high flow range. So it's good to know what that crossover point accuracy is, but you just don't want to use that crossover flow rate as your intermediate flow rate test.
Okay.
And if you find, just to add some more to that, I talked a little bit about the usage data, and if you determine that the typical usage for that meter, let's say the crossover point is at 30 gallons per minute, but then when you look at AMI or data log data, if you determine that the typical usage is at that crossover point, then it might be worth looking at the cost-benefit analysis of replacing that meter, because you know the meter is the most inaccurate at that usage rate. So you would want to seriously consider replacing that meter with either a different technology meter or maybe a different size meter, something that is more accurate for that usage.
All right. Another question here, a question that came in from a utility in Texas. We've been testing meters for the past 14 years, and we've been looking for something to help us see how to use our V2 Omni mobile tester, and can't find anything. Can you offer any advice on that?
Well, we just released a new version of the census flow verification tool, which is the software that's designed to work with the V2 tester. It's available on My Census Connection. Yeah, we can connect with that user offline for sure and get them what they need.
Sure. All right. Yeah, we have a few more questions coming in, Jeff. And for everyone else still logged on with us, feel free to submit some questions if you have any. So Jeff, on testing compound meters, you had one slide that said test at crossover and another one that said don't test at crossover. Can you cover that again?
Sure. So so the flow rates for which you want to test are low, intermediate, and high. And then if you're testing a compound meter, you definitely want to run an additional test to get the accuracy of the meter at that crossover point. What you don't want to do is use that the meter accuracy at the crossover point when you're recalibrating the meter, because that range is wider. The AWW acceptable accuracy range is wider at the crossover point. So you want to focus more on your low and high and intermediate accuracies, calculated accuracies when you try to determine how much you should add to the recalibration factor.
Okay. Question now on training. What advice would you have for getting personnel trained at being more proficient at large meter field testing?
A lot of it comes with experience from working with experienced people who've done it at that utility. Census also offers a large meter testing school. We usually do it once a year in our Uniontown production facility. Until now, we've only done it really for distributors, but we're considering opening that up to end customers, to utilities, kind of gauging the demand of that now. So I know there's comments and feedback after this presentation. So if there are people that are interested in attending a large meter testing school, please add that to your comments. Would love to see that feedback. But up until now, we've done the test pretty much on the school pretty much on a yearly basis for our distributors, just not to utilities yet, but we're reconsidering that.
Okay. Another question here. Many of our large meters cannot be recalibrated. So how does your return on investment analysis and payback calculation apply to those?
Okay, good question. So I think the benefit is pretty straightforward when you're looking at just recalibrating the testing or the meter after your testing. You see the benefit very quickly. If you test a meter that is not able to be recalibrated in the field or not able to be recalibrated at all, then it's a similar cost-benefit analysis. You just have to look more at the cost of replacing the meter itself, the total cost. So the cost of buying the meter, the cost of having to install it, the cost of shutting down water to that customer for a specific period of time. You compare that total cost to the benefit you receive from the additional revenue that you're going to get by replacing that meter. So if the meter is 20% off, you're going to get a lot. Your cost-benefit analysis is going to show you maybe you want to replace that meter sooner or later. If the meter is registering 97% accurate, maybe you want to wait longer. Maybe your analysis would tell you to wait longer on that meter. So it's still a cost-benefit analysis, and you can figure out a return on investment, but the cost is replacing the whole meter versus just testing a meter and recalibrating.
Sure. All right, Jeff, maybe one more question just to sum up some of your thoughts here. In general, obviously, meter maintenance is a huge consideration for every water utility. They're an enormous cost, and utilities depend on meters for their revenue. Just based on your experience in the industry, can you give any of your thoughts on just kind of the importance of regularly testing meters? And I know you mentioned some of this in your presentation, but just how often, just kind of as a general rule of thumb, utilities should look to do it, and just sort of the importance that they should place on that. On doing that, and maybe even a follow-up to that, like just if you think it's done efficiently enough in the industry today, like is there room for improvement generally at a lot of utilities?
I think in general, the number of utilities that have a very specific regimented meter test program is pretty low. From most of the utilities that I've talked to, the ones that start a program and keep it going consistently are amazed with the improvements they see in their revenue from testing these meters. A lot of utilities might not even have the visibility of how inaccurate some of the older meters especially have become, and how changing out one meter or testing and recalibrating one meter can sustain itself and basically pay for itself in the program and pay for the testing of a lot of other meters.
Sure. All right. Well, yeah, that's some great perspective. Jeff, thanks again for your presentation. It was a pleasure having you with us today. So if there are any more questions that come in as we're signing off here, we will certainly work with Jeff to get those answered offline. Once again, thanks for the presentation. Thank you to Census for sponsoring today's webinar. It was, like I said, great to once again get their perspective. So this webinar. If anybody missed anything or would like to refer back to anything, will be archived on our website, waterfm.com. So with that, we'll go ahead and sign off and look forward to having you back on the next webinar.